keeping the community active. And I want to thank them again for inviting me to give this talk. So the subject is Weyl-Kondo Semimetal, and I'll explain this word how as I go along. So the outline of this talk is I'm going to start off with an overview of strong correlations and quantum criticality with the particular focus of heavy fermion metals as a platform for addressing these issues. And in the process, I will explain, in fact, how we have gone from questions that come up from these strong correlation physics to meet the issue of topology in strongly correlated settings. And I'll talk in the second part, I will talk about Weyl-Kondo Semimetal with a discussion of the realization in a model, in a theoretical model, and also discussing some signatures, experimental signatures of it, which in many ways are unique to the strongly correlated settings. And I'll close the talk with a brief discussion about the outlook. And so this work has been done at Rice University with Sarah Graffey, a graduate student, and Xinhua Lai, a postdoc. But it has also been done in very close dialogue collaborations with Silke Pasching's group from Vienna, in particular her graduate student, Sammy Disaber. So, and you'll see that as I go along, there's a very informative, the theory side, the experimental side have been informing each other, and that's been a very important part of advancing this topic. So SCES, this is the community with a long interest with a host of materials, each of which would have its own building blocks for low energy physics, and heavy fermion systems is a representative of these materials, and local moments play a very important role, along with conduction electrons and the underlying interactions that respect symmetry. And we have all sorts of effects, many-body states that are of interest. And so it's clearly a very big field, with very rich physics. And the question is, are there some potentially unifying organizing principles that may underlie the strong correlation physics? And the quantum criticality has emerged as one of such potentially overarching themes, where if in the context we are discussing here, the transition could typically be between ordered phase and a disordered phase. And if you scan through the control parameter space, we know that there's amplified quantum fluctuations that can be manifested as the entropy being maximized in the vicinity of quantum critical point, and that turns the system to be soft, so to speak, and prone to developing unusual excitations and emerging phases. So I'm going to use the heavy fermion metals as the platform for illustrating some of this physics. Most people in this audience probably are familiar with Kondo lattice models, heavy fermion materials, but let me just briefly introduce the ingredients. We have a lattice at every side. There's the local moment, and there's a band of conduction electrons. Local moments can interact with each other, and two species of spins are coupled through the Kondo coupling. And so from the perspective of low energy physics, spins are part of the building blocks. And there's a competition between the Kondo coupling with the spins of the conduction electrons and the interaction which couples between the local moments, the RKKY interactions. Now, a problem of this sort, in the end, one of the central ingredient in addressing the ground state is the fate of local moments, and they could end up doing a number of different things. So for the heavy fermion field, the canonical setting is that the Kondo interaction wins. So in the end, there's a spin singlet, the Kondo singlet, that's formed, and so the local moment and the conduction electron spins are entangled. And if we have a finite amplitude of this static Kondo singlet, this correlation in the ground state is manifested in the excitation spectrum, in the sense that the local moment, and one could think of local moments and the conduction electron to be bound into a composite fermion. And when that happens, in the excitation spectrum, the Kondo interaction ends up effectively like hybridization, where you have this composite fermion which is hybridizing with the conduction electrons. And so from historically the perspective of the conduction electrons, this composite object, this big particle here, would create a resonance in the spectrum, in a single electron excitation spectrum. That's why it's usually called a Kondo resonance. But from the overall excitation spectrum perspective, it's just that you have the composite fermion and the bare conduction electron that's hybridizing with each other and forming the hybridized heavy fermion bands. And so that's the canonical understanding about how though you have the spins, local moments, the system in the end is a ground state. The ground state is paramagnetic, metallic. It's a heavy fermion and with hybridized bands. But in this harmatonia, there's also the RKKY interaction, and that could win when it dominates over the Kondo coupling, and it could form anti-ferromagnetic order or some other forms of ground state for the quantum magnet. And when that happens, the tendency of forming singlet of the local moments with the conduction electron, that desire is reduced or even completely suppressed. And so that's another ground state that one can have. And so in fact, considerations of this kind, of this competition between the this end where the RKKY interaction dominates, and or the other end where the Kondo interaction wins over, leads to a very rich phase diagram. And one way of organizing it is to use for the zero temperature phase diagram using two axes. One is the Doniak axis, that's the Kondo versus RKKY competition, which I already just described. But one could also have some sort of quantum fluctuation axis describing the dynamics of the local moments. And so in the usual case, when the Kondo coupling dominates, one forms this heavy fermion state. It's paramagnetic, and when in the other end, it's anti-ferromagnetic ordered. But one could also look at the competition vertically, where the quantum fluctuations induced by, say, frustration or reduced dimensionality would also suppress the anti-ferromagnetic order. So genetically, we have a region which is anti-ferromagnetic order, the ground state, and a region which is disordered in a ground state magnetically. And in a Landau prescription, that would be the only phase boundary. But if we think about the Kondo effect and its destruction, that leads to when we have the composite fermions floating around, Fermi surface becomes large because the Fermi surface formation would incorporate both the conduction electrons and these Kondo resonances, and there's one per site in the simplest case of these models. This would be a large Fermi surface with small Fermi surface. So considering long-range anti-ferromagnetic order versus its absence, large Fermi surface versus a small Fermi surface leads to this type of overall phase diagram. And what I want to, and since this global phase diagram will play a particularly important role in motivating what we've been thinking about meeting these correlation physics with topology, let me just expand a little bit on this global phase diagram. So if I have a phase diagram like this at 0 temperature, I could take different cuts, 1, 2, 3, and that would represent different sequence of quantum phase transitions. So trajectory 1 would be that the suppression of the anti-ferromagnetic order coincides with the Fermi surface change from small to large. And you can ask the question whether it's a first order, second order phase transition, and there's been model studies to show that one could have second order phase transitions, in which case the Kondo effect, the static amplitude of the Kondo singlet in the ground state would be critically destroyed at the transition as is the anti-ferromagnetic order. So this goes back to the initial considerations of Kondo lattice, of tuning of the Kondo versus RKPY. So this delta trajectory is like this trajectory 1 in this global phase diagram, and that's where there's the criticality associated with the suppression of anti-ferromagnetic order, and the criticality associated with the destruction of the Kondo singlet that happened at the same place, and that's a critical destruction, quantum critical point with the Kondo destruction physics. There's a jump of from large to small Fermi surface, even though the transition is second order, and I'll come back to why that happens. But in the meantime, there's been considerable experimental evidence for this type of quantum critical point where the magnetic ordering transition coincides with the suppression of the Kondo singlet amplitude. One is in ytterbium volume to silicon 2, where the isothermal Hall measurement has shown the crossover from one type of value to another type of value, which is compatible with that of the small Fermi surface state and large Fermi surface state. And you can track this crossover width at different temperatures, and what was found by the Dresden group, starting from work of Sergei Pashin and continued with the work of Sven Freeman. The conclusion was that over 1.5 decades of temperature, this full width half maximum is extrapolating to 0 in the 0 temperature limit. So there's a jump of the normal Hall coefficient, which so even though this is a second order quantum phase transition, there's a jump of the Fermi surface, and there's a T-star scale which at the finite temperatures which characterize this crossover. In the cerium rhodium indium 5, another heavy fermion material, it has pressure induced quantum critical point, and the quantum oscillation measurement of Anuki's group from Japan and transport measurements by Los Alamos and Grenoble have provided evidence that there's indeed a jump of Fermi surface, as here shown using the quantum oscillation frequency, and these frequencies are compatible with respectively with that of the small Fermi surface and that of large Fermi surface. And moreover, the effective mass extracted from the quantum oscillation measurement shows the tendency of a divergence, and that would be compatible with the statement that in order to have this transition to be second order, while Fermi surface jumping from large to small, the quasi-particle weight everywhere has to go to 0 from both sides, as the quantum critical point is approached from both sides, and the quantum critical point is described genuinely a non-Fermi liquid state. So one of the important distinctions of a quantum critical point that has not only the magnetic order that's undergoing continuous suppression, but also a Kondo effect that's becoming critical, is that Kondo effect involves not only spin, but also charge and single particle states. And so this is a very recent work anchored from Vienna, a Circle Parsons group involving the terahertz measurement of my colleague John Kono, and which showed that in ytterbium rhodium to silicon 2, indeed in the charge channel, there's omega over t scaling as characterized by the optical conductivity, showing a scaling collapse in terms of omega over t. And one can do model calculations both for single impurity models, both Fermi-Kondo model and the lattice Kondo lattice in terms of extended dynamical mean field theory to show that the charge channel, there's a quantity which carries charge quantum number, and it also shows omega over t scaling in addition to what happens to the omega over t scaling that's seen in this model in the spin channel. Now, so this is a trajectory one, which I spent some time describing. There's also been efforts along the way, along trajectory 2 in some cubic materials, which I don't have time to get into. But I do want to mention the ongoing effort in accessing a trajectory in this highly quantum fluctuating regime that's realized in terms of geometrical frustration. This is a material cerium, palladium, aluminum with a distorted Kagame lattice. And there's been extensive work of Hilbert Volonaisen and colleagues from Kaohsiung on this material. Recently, a group in Beijing, Peiji Song, collaborating with Frank Staglish and others from Germany, and showed that if you tune the material not only by the magnetic field, but also by pressure, that realizes two parameter tuning, and the experimental result shows that there's a range of pressure and the magnetic phase diagram in which the color scheme shows that yellow means that the resistivity, temperature-dependent resistivity, is closer to linear in T rather than to T square, which is in this red region. So there's a region of non-Fermi liquid. Precisely what the state is remains an open question, but one could put this pressure tuning and the magnetic field tuning in this global phase diagram as two axes, and consider that this non-Fermi liquid region realizes a phase which perhaps have a small Fermi surface. The dashed line marks some sort of crossover feature that shows some indication of the Hawk change, but that's most clearly seen in a scale like this. So I think what is experimentally affirmed is that there's a range of non-Fermi liquid, and tentatively it's assigned to be accessing this a cut like this in the global phase diagram. So efforts like this continue, and I remember giving a talk that mentioned a phase diagram like this. I think it was in front of Gordon Babe, and he said, "Oh, this kind of phase diagram is ideally suited for the ultra cold atomic community to simulate, to emulate." And but in these correlated materials, the question is often asked, or if I'm tuning pressure, precisely what cut it is. And usually my answer is I don't know, but in some sense I don't really care, because it will be universal and it will take a cut of that sort. But that's not particularly satisfying. So along this way, particularly in the discussions with Circle Parshin, we've thought about using spin-orbit coupling as a tuning, because you can experimentally one can do doping studies which would be isoelectronic, iso-size, and so presumably the dominant effect is that atomic number is changing, and spin-orbit coupling is being varied, and that's a dominant variation, and that would be a trajectory that is well defined microscopically. But the question is what trajectory that would correspond to on this phase diagram, and that in fact for us is the way that we've the trajectory that we followed in getting to this question of how the global phase diagram becomes different when explicitly consider the large spin-orbit coupling in addition to strong correlations. And that's part of this how, this word how in the title, how does the strong correlation physics intersect with topology. Now, from the perspective of correlation and topology, there's extensive interest from different communities. More often than not, one considers existing topological phases in the non-interacting case and switch out correlations and ask either perturbatively what happens or whether there's non-perturbative effects associated with it. Another set of questions which have been quite productive is to ask correlations to produce broken symmetry, such as magnetic ordered ground state, and the change of the symmetry would affect the type of weakly interacting topological phases that can be realized. Now, the question that we have set out to ask ourselves is, well, what about the third route? Could there be topological states which are in fact driven by strong correlations? So instead of asking the question of what the effect correlation has to the pre-existing non-interacting topological phases, we could think about a global phase diagram of the sort that I've been discussing, and switching explicitly the spin-orbit coupling to make it sizable, and ask, is there some topologically non-trivial states that pop up in the phase diagram as a part of the global phase diagram? So that's a very overarching question, and this does lead us to think about this particular topic from the perspective of heavy fermion metals. But we have to be more concrete than that. So here's a more modest goal that's more concrete and perhaps serves as a first step in along this direction. Which so the question I want to address is there a model whose ground state is topologically trivial in the absence of the Kondo effect, but becomes topologically non-trivial in the presence of the Kondo effect? So that's the concrete question to which I want to make a claim that we found affirmative answer, that there is a model and it has such features. So let me describe the model. We've been guided by thinking about the type of lattice that we want to consider, which is non-Nonsymmorphic and can break inversion symmetry and preserves time reversal symmetry. So we consider the Kondo lattice with spin orbit coupling, but specifically starting point is a diamond lattice, which comprises two FCC sublattices, and I've marked that with the black points for one FCC sublattice and the green points for the other FCC sublattice. And the middle of point here between the B sublattice point and A sublattice point is the inversion center. And so that means that I can introduce a potential that discriminates between the A and the B sublattice, a staggered potential to break the inversion symmetry. And so Nonsymmorphic lattice for the strongly correlated electron community, perhaps it's not that unfamiliar. In fact, if you take ionic tides, the 1111 systems, if you do translation from the arsenic side to the nearest neighbor arsenic sites, that doesn't preserve the system. But if you do a reflection with respect to the ion plane, you find that it's invariant. So it's marked by a discrete symmetry in the space group. And diamond lattice, it's a bit harder to actually go through, but it's the same idea. If a fractional translation multiply, in this case, by a rotation. And that discrete symmetry means that I could characterize the electronic states by the eigenvalues of this discrete symmetry. So in the diamond lattice, it was known that there is these two states corresponding to two eigen states of the discrete symmetry. It has degeneracy at the zone boundary, and in particular at the X point of the Briand zone. And so we take a model which is the canonical Anderson lattice model that's very familiar to the SCES community, and the conduction electron are living on this diamond lattice. This is the full K-Malay model with the dispersion spin orbit coupling, and add the staggered potential at m equals 0 is the diamond lattice. When m becomes non-zero, it breaks the inversion symmetry. And so we can vary the this size of m for the degree of breaking the inversion symmetry. And now we're going to have the hybridization term. The D here, in fact, labels physically the F electrons, and there's a very large Coulomb repulsion on these F electrons. And in fact, we're going to take the limit that U is the largest scale in the problem and going to the infinity limit, and do some saddle point analysis where the physical electron is expressed as a product of the spin carrying object and the slave boson. Filling is an important part of the model, and we're going to take the quarter filling case, meaning that at every site, the total number of electrons is on average 1. So let's ask what happens first when there's no Kondo coupling, when the two species are decoupled. And first, when the inversion symmetry is preserved. So in that case, the conduction electron band and the F states are decoupled, and the conduction electron band respects the dispersion respects the space group symmetry I just described. So there is a degeneracy at the X point. It's at the Dirac point. However, I have 1 electron per site on average, and that electron wants to go to the F orbitals, and because it has low energy, and make it half filled, and in fact, it's a Mott insulator, and there's no electron left for the occupying the conduction electron band, so it's empty filling. Similar thing still happens if I switch on the staggered potential. now it breaks the inversion symmetry, and there's still no Kondo coupling. The two species are decoupled, and when that happens, the Dirac point in the at the x becomes certain number of pairs of Weyl nodes, but the conduction electron band is completely empty, so it's a trivial band insulator. So in the end, this state, the ground state, is topologically trivial. Now, on the other hand, when the Kondo effect happens, when the Kondo scale is small but becomes non-zero, then in addition to these conduction electron dominated states that still has a bandwidth of d, the bare bandwidth, which is the notation I've used to describe the bare bandwidth. There is also these hybridized bands, which have an energy spread of kb times tk, and the Kondo scale, remember, is very small, and it's about 3 orders of magnitude smaller than the bandwidth. So this is a narrow band. But these bands still will respect the dictation of the symmetry, space group symmetry, and there could be Weyl nodes in these heavy bands. And so we, in addition to the nodes that could be adiabatically connected to what happens in the conduction electron band, in the absence of Kondo coupling, there are now these Weyl nodes which are generated by the Kondo effect, but they are pinged. First of all, they are pinged in the vicinity of Fermi energy because they have to happen within this narrow band. And if we have this filling that I've chosen, the quarter filling case, in fact, has to be exactly at the Fermi energy. So we end up with, in this model, that the Kondo effect drives these new sets of Weyl nodes, and ping the Weyl nodes to exactly to the Fermi energy. And that's part of what's important here, because if I go beyond the saddle point analysis, these fermionic excitations will acquire finite lifetime. However, if these nodes are pinged to the Fermi energy, these Kondo-driven Weyl nodal excitations are long-lived, and so they are sharp excitations, even though this is a strongly interacting system. And we can verify this. We think further that these are indeed Weyl nodes in the saddle point calculation by calculating distribution of the Berry curvature, and to show that these nodal points in the dispersion, in fact, are the sinks and sources of these monopoles in this Berry curvature distribution. So that in the bulk spectrum, these are indeed linear dispersing excitations controlled by the nodal point that has characterized by singularities in the Berry curvature distribution. One can also calculate and we did to show that there are Fermi arcs with a dispersion which also spreads over a scale of the Kondo scale in narrow bands. And so the consequence of these Weyl nodal excitations having a dispersion that's controlled by the Kondo scale is that the velocities will be much reduced compared to what would be the case in the non-interacting systems, much reduced by several orders of magnitude, and that will be important in terms of considering experimental consequences. Another point which I want to mention is that this Berry curvature distribution, the singularity in the vicinity of Weyl and anti-Weyl nodes, one could vary the model somewhat. I've described a model where the Weyl nodal, the nodes are not tilted, but we can introduce some additional terms in the dispersion of the model that is compatible with the space group symmetry and leads to tilting of these Weyl nodes. And so this is illustrating here. Here the occupation is not exactly quarter filling. It's slightly deviated from 1 by a small concentration. So that leads to Fermi pockets, which are tiny. This is the area that correspond to this small region in the Briand zone, or more precisely in the this zone, the cut of the three-dimensional Briand zone boundary, including the X point. And without tilting term, it's essentially symmetrically distributed. But once one introduces tilting term, the Fermi pockets is this dashed line. It's very asymmetrically distributed with respect to nodal point. If I zoom in further, and I can see that even more clearly, that it goes from essentially symmetric Fermi pockets surrounding the nodal point to be very asymmetric. And that also will be important in considering the experimental consequences. And I want to just mention that one could introduce variations of models, including variations of filling, change of lattices, and realize a number of different kinds of these topological Kondo-driven semimetals and transitions into, for instance, the Kondo-inserted phases. And at the transition point, there's interesting aspects of dispersion, such as quadratic band touching, which I'll not get into in this talk. Instead, what I want to do in the remaining time is to consider the signatures of the Weyl-Kondo Semimetal. And I've presented in a way that, that starting from a model side, but in reality, we've had this slide of the theoretical considerations have very much gone hand in hand with the experimental studies by the Vienna group in the material, which I'll introduce very shortly. But let me just organize the signatures that collectively we've thought about into 3 categories. One is to probe this linear dispersion. So in the usual non-interacting, weakly interacting Weyl systems, one would do APES, but APES is challenging for these narrow band systems. And so we want to think about how to probe linear dispersion. And so experimentally, the material that's being studied is Cr3 bismuth 4 palladium 3. The platinum version has been now studied as a Kondo insulator in this community. The palladium version is new as a heavy fermion system, and it's cubic, it's nonsymmorphic, it's non-central symmetric, and there's no magnetic order, and based on transport, it's a semi-metal. And so I'm showing here the result from Circle Pasching's group on entropy on the specific heat. And if you plot the specific heat versus divided by temperature versus T square, you see that it has low temperatures has a linear dependence and intersect in the 0 temperature limit the value for phonons, but at the non-zero temperatures there's excess contribution. So this is the electronic contribution that C over T goes to 0 in the 0 temperature limit, but at low temperatures has this T square behavior. So the T cubic, and there's a lot of entropy in it, which means that the Kondo scale is roughly somewhere around 13 Kelvin, I think is a precise number that's being extracted, but on the order of 10 Kelvin. And so T cubic is a characteristic of linear dispersion, except that usually one cannot see it because phonons dominates. But here, the prefactor for T cube, which is inversely proportional to renormalized velocity square, because of a reduction of velocity by several orders of magnitude, it becomes possible to see the electronic contribution, right? So theoretically, one can make a statement that going beyond the saddle point analysis, including residual interactions, this T cubic form is still robust, and there should be large enhancement. And that's what experimentally is seen. So the entropy, which is what the SCES community always does, in fact, provides a way to, as sort of replacement of R tests for seeing the linear dispersion. Now, in addition to dispersion, we would like to see the topological character. And importantly, since in the model, in this Kondo-driven Weyl-Semimetal state, the nodes are pinged at the Fermi energy. So we will have Barry curvature singularities, which would be very large near the Fermi energy. And so there should be some signatures. Precisely what was not clear, and this was a discovery by the experimentalist who measured the Hall response and find that even in the zero field limit, there's a very large sigma xy. In fact, it's gigantic because the tangent of Hall angle is like 0.5. And experimentally, it was demonstrated that time reversal is preserved, that there's the MUSR doesn't see any signatures of spontaneously generated magnetic order. So in this time reversal, microscopic time reversal state, invariant state, there's a very large spontaneous Hall effect. So what is that? The experiment further shows that this regime where there's this giant spontaneous Hall response is accompanied by, in addition to the usual odd in magnetic field response of rho xy, and even in magnetic field component, and it persists to certain characteristic magnetic field, which I'll come back to. So the way to think about it is that this is essentially the replacement of the chiral anomaly probes of the topological character of the wire nodes in weakly coiled settings, except that longitudinal magnetoresistance is not a good quantity to use in these Kondo systems because the Kondo effect themselves dominate the magneto resistive transport response, the magnetoresistance, but the Barry curvature singularity, as highlighted by this plot of omega in the very large blue, very large red region, means that there's a very large Barry curvature distribution. And if the Fermi pockets is asymmetrically distributed in the vicinity of node, it should be picked up in transport quantities. And indeed, one can think of this spontaneous Hall response in terms of contributions of the anomalous component of the velocity, which is E times this omega, the Barry curvature, which show, and if you use that part of the velocity and calculate sigma xy, one gets a term which would be 0 in equilibrium, but as soon as the system is driven out of equilibrium, say by an electric field, then the non-equilibrium distribution would allow this sigma xy to be non-zero even at 0 magnetic field, something that in the perturbative formulation was done by Soderman and Fu. And the twist here is that because the Barry curvature singularities are happening so close to the wire node point, and the Fermi pockets is presumably tiny, that one can easily drive the system in a truly non-equilibrium regime. So the rho xy versus the current can go beyond the weak field region very readily. And if you look at the details of the results in 1 omega, 2 omega response, etc., would be the experimental results compatible in to be in this fully non-equilibrium regime where one expects one can see that the this Hall response will be gigantic. So that's the flavor of the second type of signatures. The third type of signature is to take advantage of the fact that this energy scale is small, which limits RPES, but can be advantage here because this is the Kondo scale is something that I can easily sample by tuning laboratory magnetic field, for instance. And so the notion is that if these are wire nodes, one could readily tune them and maybe even annihilate them. And I already alluded to that this even in field component of rho xy that's seen experimentally in cerium-3 bismuth 4 palladium-3 at the low temperature limit extends to about somewhere between 6 and 9 Tesla. So what does that scale mean? And experimentally, this has been studied in some detail. I'm not going to go through the, there's a number of different features happening, but to make a long story short, there are 3 field ranges. There's the field range, which covers where this even in field signal is experimentally observed, and then it goes away. But then there's a scale beyond which the Kondo-like physics in the large mass, as shown up in the large quadratic t-squared dependence resistivity coefficient, strongly increasing, the Fermi liquid scale coming down, looks very much like the canonical quantum critical, like heavy fermion physics. But the question is, so this transition is reasonably familiar to this community. The question is what that is, where the carrier number is significantly reduced, going from this region here to this region 2. So our interpretation is that this field scale here signifies annihilation of the wire nodes. And so Sarah Griffey has done calculations of the model, which I described to you earlier, but now add a Zeeman coupling in particular to the local moments. And there's a number of different things happen as one increases Zeeman coupling, but there's a threshold value in this model where all the nodes go away. And this is a threshold value which is on the scale of the Kondo energy, but still some fraction of it. And we can still talk about the Kondo physics when this is happening. And so at the zero field, the X point, its vicinity, where the wire nodes happen, as I described several times earlier in the talk. If we introduce magnetic field, it follows a trajectory, eventually goes from the boundary at the Brillouin zone to the interior of the Brillouin zone, and further goes to some threshold. There's some new branches of these wire nodes which are developing, but eventually, as one approaches the threshold value, all these nodes, they march towards the gamma point and eventually pairwise annihilate. And that's what this threshold value. And that's a topological phase transition. There's some details like quadratical band touching, etc., that happens. But the important point is that a magnetic field that corresponds to a Zeeman scale on the order of the Kondo scale can be large enough to control the nodes and annihilate the nodes. So that's pretty much what I want to say. Let me just mention what I think is that we've only seen the tip of iceberg. The number of questions one can ask. What are other other materials against be used for this kind of study? So the Zhejiang group has been looking at this ytterbium bismuth platinum. There's some hope that cerium ruthenium 14-6 also belongs to this category. And there are other materials where wire-like features have been observed, but to what extent these are really heavy fermion systems remains to be settled, and one could add to this category of materials a number of others. So I think additional materials probing different aspects of this semi-metal physics, that certainly will be a direction that will be seeing active activities. from a general perspective, I started off by saying that there's a global phase diagram that helps us to think about the correlated electron physics. And one would like to ask whether that's and how that's enriched by these topological phases. And the flip side is that does this type of setting provides insight for strategies for realizing and exploring strongly correlated topology. And so I leave those both of them more or less as a question. The first is, could one study concrete models for the global phase diagram and see how these topological non-trivial phases are part of the phase diagram? What are the transitions, and what correlated electron physics they can influence if they exist? For instance, what kind of if superconductivity develops in the vicinity of this kind of phases, what's the nature of the superconducting state? Or maybe, for instance, Los Alamos group has been looking at some of the canonical heavy fermion superconductors and asked, if you go far away from Fermi energy, could one find nodes? And if one find them, one could find a way to tune them to the vicinity of the Fermi energy. So I think this is a promising direction. The flip side is that we would hope that we don't just use topology to help correlated electron physics. Can we also do the opposite to provide some insights on general strategies of realizing strongly correlated topological states? And the kind of model and the experimental studies I've described provide a motivation to think of one such general strategy, which is that strong correlations cooperate with not only spin-orbit coupling, but also space group symmetry. So for instance, focusing on the non-Symmorphic space groups in choosing what the materials to look at. But theoretically also, there's a variety of models one could study that has the ingredients of both strong correlation, spin-orbit coupling, but also the right kind of space group symmetry. Are these the way, so for the correlations and topological type of ingredients to intersect and to cooperate and produce correlated topological states? So these are this is clearly a direction that's very much worth future work. And I should just mention that the non-Symmorphic symmetries as an example of these interesting space groups is not a rarity. In fact, if you look at all the space groups in 3 dimensions, the majority of them are actually non-Symmorphic. So with that, let me just summarize what I actually said in this talk. After motivating the study, I showed a model that is defined on the non-Symmorphic lattice with the right filling. It has a Kondo-driven wire nodes that are pinged to the vicinity of the Fermi energy, and therefore these are the nodal excitations which are sharply defined. And I briefly mentioned the CR3 bismuth for palladium-3. I didn't really do justice to experimental work. You'll have to hear Silke Sami to talk about this material. I did give a hint of what kind of signatures of these strongly correlated topological semimetals, in particular Weyl semimetals, could have. They are quite different flavor from what are typically emphasized in weakly correlated topology. The small velocity leads to the consideration in terms of entropy, and nodes being pinged to the vicinity of Fermi energy leads to this consideration of giant spontaneous Hall effect. And in fact, what actually happens is the other way around. Experimentally really just discovered this. The theory this tried to catch up on this. But also the small energy scale affords control of this kind of characteristics, and that is also a very interesting aspect. This very amplified response of these states which are driven by strong correlations, and from a perspective of functionality, maybe that's an advantage. So with that, thank you very much for your attention.
Okay, thank you very much, Qimiao, for a very nice talk. So we should go for the questions now. So we will start with the questions from the Zoom meeting environment. So please raise your hand if you have questions using the raise your hand options. So I don't see a question here. Let's see if we have questions at the Google Meets.
Oh no, there's a question. There's somebody raised a hand.
Okay.
Pradeep?
Yeah, go ahead.
Can you hear me?
So Pradeep, yeah, turn on your camera and mic. Go ahead, please.
Hi, Pradeep. Yes, I see you.
Yes,
and I hear
okay.
you.
So the question is, what is the size of the velocity near the Weyl point, or rather, what you measure from the specific heat? So I guess the question is not necessarily to you, but just in case you know it. What's the order of magnitude of velocity?
It's only, so I showed you the specific heat. Somehow I've lost control of the slides. Happened to me earlier. But the answer is yes. There's a value that's extracted, and the velocity. Normally the electron velocity is much larger than the sound velocity, right? And that's the reason if you have nodes, you have T-cubic component, you just cannot see them in this context. But here, it's almost on the same order of magnitude, to the zeroth order. So one can fit the electron contribution by the expression, which is somehow my system is not allowing me to switch back to in a slide. That you can fit the T-cubic coefficient in terms of the renormalized velocity. And if I remember correctly, Circus group got something like 1,000 meters per second. But anyway, it's on the order that of the sound velocity.
Oh, so this is still large, and on the other hand, it may be
much smaller. Sorry to interrupt you, but it's much smaller than the bare electron velocity.
Right. But it's really a little large for sound propagation, rattling of these symmetries.
Yeah, I think I see where you are getting at. But the point is that one is reaching that.
One is reaching that, yes.
Yeah, and
that there may be materials where it happens to.
Yeah. So basically, this is a material. The Kondo scale is about 13 Kelvin. And there's could be variation of materials which one's already at a doorstep in terms of the kind of velocities that you want for I think what you're thinking about. Right.
Thank you.
Okay, so Qimiao, when do we have a questions at the Zoom meeting? Could you repeat the questions so everybody can hear? In the Google Meet as well, okay?
Yeah, I will do that.
So let's see if we have a questions at the Google Meet environment. Is that a question? Any questions at the Google Meet environment? No. So Maria, can you ask a question that is in the Facebook environment, please?
Yes, I'll just connect my mic. 1 second. Can you see me? Hi.
Yes, I do. Yeah.
Okay, so I'll read the questions from Facebook. Just wanted to let you know that we had almost 250 persons in all the environments. So it's quite nice.
Okay.
Let me see here. Okay, so we have a question from Julio. He's from the University of São Paulo here in Brazil. And he asked, conditions of topology and Kondo lattice plus SOC of time reversal symmetry broken means the realization of materials that do not undergo to magnetic order disorder transitions?
Let me repeat the question too, and if I didn't get 100% right, please correct me. So the question is the condition that I discussed, which is time versal symmetry is preserved.
Yes.
And there's a Kondo effect, there's spin orbit coupling. Does this kind of physics connect in any way with the magnetic, non-magnetic transition in the phase diagram? I think that's the question. It's a very interesting question, very important question. It's really, the way I see it, it's part of the ingredient of putting, the kind of physics I discussed in the overall global phase diagram. So the short answer is we don't know what happens. At the moment, this particular model that we have studied, the particular material, Cerium-3 bismuth for palladium-3, the regime that's being studied, non-magnetic, but clearly it's strongly correlated, and there's heavy fermion physics. So if you think in terms of overall strong correlation physics or the heavy fermion phase diagram, one could ask the question, how far away is the magnetic order? So sure, that's I think very much research for the future. It's something to keep in mind. But for instance, in the 343 material I mentioned, the experiment shows that's non-magnetic, but maybe there's some cousin materials which is magnetic. Right. So that's a very interesting, important question for the future.
Okay. Well, he says greetings and nice talk.
Thank you.
Okay, so we have Anas Omer from the Leibniz University Hanover in Germany. And he asks, if I understand correctly, the model of Kondo lattice plus SOC is two-dimensional. How about systems that can be effectively one-dimensional?
So the question, I think everybody heard, but just in case, let me repeat. The question was the model of the Kondo lattice on this diamond zinc band lattice that I specified. The question was, is it two-dimensional? The answer is no, it's three-dimensional. But I think the more important aspect of the question was, is one-dimensional model version of related models interesting? One dimension probably has different aspects of topology to be considered, and it would be interesting to study what kind of phases one could have for this kind of model in one dimensions with spin orbit coupling, and I would encourage work along this direction.
Okay, so any further questions in the Zoom meeting?
We have one more in Facebook.
Okay, go ahead, Maria, please.
Okay, so we
please
have a question.
Say the name, surname,
Yes.
and affiliation of the participants, please.
Yes, so we have Juan from Austin, Texas. He asks, since the Kondo band is narrow, what kind of non-linearity do you have to account in computing Hall coefficient? Is it necessary to go beyond the semi-classical Boltzmann transport formalism?
Yeah, so the question, yes, well, thank you very much for related question, but the question was, since these Kondo-driven heavy fermion bands narrow, the nonlinearity that I mentioned in the Hall response and zero field, what kind of approach that can be taken to study it. And so there are two aspects. One is that I think that's the question, the premise of the question, which is in fact what we have qualitatively considered, that it's not so much that the bandwidth, it's a narrow band per se, but it's more of this narrow band, the Kondo physics pings, the Kondo physics that underlines the narrow band. It pings these Kondo-driven wire nodes to the immediate vicinity of the Fermi energy, and therefore the Berry curvature singularity is happening in the immediate vicinity of the wire node. So if I drive it, it would create a non-equilibrium distribution that is readily in the non-equilibrium regime. So that kind of qualitative consideration allows us to rationalize what has been seen experimentally. But at this stage, in fact, it's an experimental discovery because it's very hard to actually set up the non-equilibrium formalism to determine the specific distribution function that allows for quantitative calculations. And that's very different from the weakly correlated cases where, in fact, this Berry curvature anomalous velocity driven spontaneous Hall effect leads to what's called the Berry curvature dipole, and one can even do LDA calculations for that. So at the moment, the quantitative non-equilibrium physics in such strongly correlated setting, it's a very hard problem. It should be done, and it's very much, again, a problem for the future. So it's a great question.
Great. Do we have more questions at Facebook, Maria?
No, we have no more questions here.
Okay.
They just thank you for the answer.
Thank you.
Okay. So I don't see questions here at the Zoom meeting. So I would like to ask a question, if I may.
Yeah, please.
So Qimiao, so using this last slide, when you describe the properties of a Kondo-driven Weyl nodes or in Kondo Weyl material in general, are there any crystal field wave functions that could make the material favorable to show non-trivial topology or Weyl nodes in the near the Fermi surface? So should I look for any crystal field wave function, ground state in particular, to find these properties?
Right. So so the question from Pascal was, are there some sort of variations of the crystal field, both the, I suppose, both the wave functions of these local levels and the distributions of it that could first of all make a difference and also change the conditions for realizing this Kondo-driven type of Weyl states. Is that a fair rephrasing of your question, Pascal?
Yeah, perfect. Thanks.
So that is an extremely interesting question. I think there are two aspects to it. One is that suppose one stick to the kind of scheme that goes into the studies that have been done, which is like there's a Kramer's doublet, and you could have some higher levels that sitting at certain energy separation away. At the moment, that's more of a means of tuning the correlation physics. For instance, in Cerium 115 materials, where you are in this global phase diagram appears to be tuned by the variation of the wave functions of these Kramer's doublet, and I think somewhere between these considerations of the Los Alamos group and the Cologne group, who actually have measured this kind of wave functions, have led to considerations of that sort. In our model, we haven't really considered this effect, but it could very well be that as one tunes where if I put the phase that was realized through variations of the underlying model or studying also other phases in the global phase diagram, that could very well come into play. So it's a great question. It's sort of part of the things which are still hidden below this tip of the iceberg that has been looked at. But I think there's also a second aspect of the question, which is that, suppose it's a 3D material, suppose it's not the Cramer's doublet, suppose it's some other forms for ground levels. Are there some new physics that can come into play? And in fact, again, that's an extremely interesting question, because if you think about the symmetry indicators in weakly correlated topology, and what kind of levels are part of the ingredient to think about the symmetry indicators. And I expect that the future work may very well sort of uncover some physics that's associated with what difference that change of the crystal level schemes could produce in terms of the type of correlated topological like phases that can be realized. So it's a great question, and it's an ingredient for future work.
Okay, thank you. Because actually I remember that for Samarium B6, there was some claim that the gamma-8 symmetry was important to bring non-trivial topology in that case. So I just wonder if that could be a general effect, that if you have a gamma-8 ground state for cubic compounds that are strongly hybridized, the symmetry of the gamma-8 combined with the symmetry of the Fermi-surface can actually help to have a non-trivial topology.
If you have gamma-8 levels, you're going to grab different set of conduction electron states into play in a low energy physics, and that's part of the ingredient, and that's the kind of variations that models of this sort coming from these F electron systems we have more of experience in dealing with this variation and enrichment that comes from the crystal levels.
Perfect. So thank you. So any Jakob, go ahead. Qimiao, can you hear Jakob Kopelovic?
Yes, I do. Hi.
Go ahead, Jakob. Ask your question.
Yeah, so maybe I can paraphrase the question first. So the question was that this zero field Hall response, is that necessarily due to effects such as Berry curvature or other anomalous Hall effect? Could there be some other reasons for it? Is that fair representation of your question? Correct. Yeah. So for the mechanism I described, it only happened perturbatively. It's a nonlinear response, right? you drive the system. So the microscopically, the system has the time reversal symmetry invariance. But once you drive it, macroscopically it breaks time reversal symmetry. So that's why in a nonlinear response, you can have this effect even at a zero field. Now, there could be some other reasons. So for instance, imagine you can have, say, in literature, there's some discussions of more mundane type of effect. If you have a broken rotational symmetry, like some kind of nematic phase, then the different principal values of the usual current components will no longer be an identity matrix if you write the current as a matrix, and you could generate a zero field Hall response just by ordinary velocity instead of an anomalous velocity. So that would happen if imagine that you have a nematic order, but in this material that I mentioned, or in our model, we certainly don't have anything like that. So one could enumerate through these normal velocity contributions, and they just don't apply here. So far, and also, the size is gigantic. It also only sets in. It doesn't exist at high temperatures. It really only develops in the regime where the Kondo effect is happening, right? So all these different features I mentioned in the experiment, the effect is hardly observable above 3 Kelvin, but is really observable at 3 Kelvin and below. So all these systematics provide, and the giant magnitude of it, provide evidence that the 03 bismuth for palladium-3, what's being observed is coming from the anomalous part of the velocity, not the normal part of the velocity. Yeah. Yeah. The point is that so the question was I'm not sure I got the question 100% right. So let me just let me paraphrase. Yeah, please. Yeah, you want to add to that? So the question I thought was that suppose you're at a zero field. Of course, if I apply magnetic field, I break time reversal symmetry, right? But if I at a zero field, I'm not breaking the time reversal symmetry. So what other nodes are the why it's Weyl instead of Dirac, or was your question the other way around? So the point is the following. In fact, I went through that sequence. If I preserve, without breaking the time reversal symmetry, if I preserve the inversion symmetry, then I would have Dirac nodes. But once the inversion symmetry is broken, then the Dirac node is split into pairs of Weyl nodes. And so in the model that we have studied, we started from that. We already, unfortunately, I couldn't get back to the to the slides. I wish I could. Oh, I can. Sorry.
Yeah, just share your screen again, Qimiao.
Okay, great. Let me do that. Let me get to the Zoom and share the screen. Do you see that?
Yeah, perfect.
Okay, great. So the point is, let me maneuver
Just one thing.
Okay, here we go.
People
Yeah.
from Facebook are not seeing the screen.
Ah, okay, I'm sorry about that. So, but let's see, what can we do? Maybe I'll just
Yes,
describe in
perfect.
words. So the point is that at the zero field, I've started in a model where the inversion symmetry is already broken. So for instance, on this surface, there are these pair of wire nodes instead of Dirac node at the X point. And now on top of that, what we've done is to introduce time reversal symmetry breaking by the Zeeman coupling. And so what I think something is happening. Do you see the screen?
Yeah. No, you should
No.
go to the presentation again. We're not seeing the presentation anymore.
Stop others.
Yeah,
okay.
Maybe just stop sharing and start sharing again.
Okay. Continue. Okay. So the point is, I think I just okay, great. Yeah. So the point is that if I already have broken the inversion symmetry, now I introduce time reversal symmetry breaking by the Zeeman coupling. It doesn't change the type of nodes, or at least initially, it just moves. And then it moves to different paths. So from here, the starting point where there are wire nodes to the point where eventually all such linearly dispersing nodal excitations, the nodes go away. There's in fact a sequence of changes in different range of the Zeeman coupling. The characters of these nodes and where they are different. And so that perhaps is what your intuition was suggesting, that if you break the time reversal symmetry, starting from inversion symmetry breaking, something has to happen, and it does. And there's a sequence of this evolution of these wire nodes until the point where it eventually goes away. They all meet at gamma point. So it's a very interesting question. What's the topological characteristics in these different regimes? And I think that was a very interesting question. Yeah, thank you. Yeah.
Right. Is there any further questions at the Zoom meeting? Maria, in the Facebook, we do have questions.
Yes, we have one.
Okay, go ahead, please.
Okay, so we have a question from Varun from Cambridge. He says, regarding node control and annihilation, is the energy scale in MAV, could terahertz radiation be used to manipulate or control this effect?
So the question was in terms of the kind of control and annihilation of the nodes that I talked about. The question was if one introduced radiation, say terahertz type, whether that's a way of added control, or is also a way to control. It's a great question, and that requires so it depends also on whether a bunch of frequencies or single frequency that's applied. In some cases, one can still, it's easier to do analysis in almost the equilibrium formalism. In other cases, you have to really drive the system, and becomes a truly non-equilibrium problem. Regardless, so again, that's a great direction to pursue. Yeah, it hasn't really been studied. In graphene, for instance, where one has Dirac to begin with, of course, the scales, energy scales, are very different, but there have been extensive studies of what happens when radiations are introduced in this strongly correlated settings. It's a somewhat harder problem, but probably it makes it even more interesting problem. So again, that's I feel like there's so many of these questions that being sort of categorizing as the below this tip of iceberg that's being seen category, and that's certainly experimentally one should probably just do it. It's an exciting way of exploring it. Theoretically, we'll catch up. We'll try to. Thank you.
Perfect. Any further questions, Maria?
In Facebook, no, but we have a question in Meet.
Okay, go ahead, please.
Should I read it too, or should I let him ask?
You should yeah, he can ask if it's
okay,
possible
Jean,
to turn.
You can turn on your mic. Is he still here, maybe? Yes, he's still here. Your mic is not working. Okay, so I'll read
just
it.
read the question.
Okay, so he's Jean here from Unicamp. Is it possible to a system to have a Kondo-driven topological phase transition from a type 1 Weyl semimetal to a type 2, for example? In other words, is it necessary a trivial ground state for the non-interacting analog, or a different topological ground state can fulfill this condition to have a Weyl-Kondo Semimetal? Sorry.
Yeah, so I think the question was in this Kondo-driven Weyl phase, could there be transitions from type 1 to type 2 type Weyl nodes? This has to do with different amount of tilting. And so the short answer is, I'm theorist, so the short answer is yes. In a model, we can very easily do that. But it goes back to the kind of issues I was raising in the correlated electron physics part in terms of tuning. If there's a model where I can tune the tilt potential, for instance, what in experiment in materials, what can one really do that would correspond to that? Yeah, one could always look at cousin materials of, and that's a discrete variation. So the short answer is yes, it can happen. I certainly can vary the terms in the Hamiltonian in this Kondo lattice that go from type 1 Kondo-driven Weyl type of nodes to type 2 Kondo-driven Weyl nodes. And I alluded to that we could have variations of models which could also have other nodal types in the solutions, and it would be fascinating to see whether there are materials which would allow that kind of topological phase transitions to be explored, especially if one can do that through continuous variations other than in real materials as opposed to be in the emulating synthetic type of structure. So that's a fascinating question. It's an open question as to whether experimentally it's feasible or not.
Okay, thanks, Qimiao. We have a question from Zakir Hossein. Please, can you turn on your mic and ask the question, Zakir, please?
Thank you, Qimiao, for a nice talk. I have a simple question. So, in the context of magnetic topological material, people talk about topological Hall effect.
Mm-hmm.
So, topological Hall effect. So, my question is like the giant spontaneous Hall effect that you are talking in the context of correlated topological material. Is it like the topological Hall effect enhanced strongly due to pinning down of the nodes at the Fermi surface? Can we think in terms of that?
Well, first of all, good to see you. We're just at a different conference. So the question was in the weakly correlated Weyl systems, there's the effect in magnetic ordered systems. There's a topological Hall response. Is that related to the kind of Hall response I was describing in this Kondo-driven Weyl Semimetal context. So the short answer is that's very different, because here time reversal symmetry is preserved, while usual context that you refer to breaks microscopically in the system, breaks the time reversal symmetry, and that's why there is the usual effect of the topological Hall response. And now, of course, ultimately, they are all connected to the anomalous velocity, but the mechanism is really very different. Here, it's a zero field, and it's really non-linear in electric field. So in the weakly correlated materials, there has been no study of this zero field spontaneous Hall response in Weyl systems. There has been some studies in materials that 2D materials, layers of multi-layer materials that break inversion symmetry to see this nonlinear effect that's based on this Berry curvature dipole. And it actually came out about the same time the experiment in CN3 bismuth 4 palladium 3 was found, and the result was found. And but the effect in that case, without a singularity in the Berry curvature distribution, the effect is much smaller. It's fascinating to see that in those systems. So here, the tension of the whole angle, it rises to the level of 0.3, 0.5. There, the observed effect is like 10 to minus 4. And in part, there's no amplification due to the pinning of the nodes, and in part, main part, because there's not even singularity in the Berry curvature distribution in the materials in which such a zero field effect has been seen that in materials that do not break the time reversal symmetry. So the really important ingredient here is, in addition to the effect being giant, is that the underlying system preserves time reversal symmetry. And in that sense, it's very different from what is normally seen.
Thank you. Thank you.
Perfect. So any further questions in any of the environments? So I don't see any further questions. So Qimiao, I would like to thank you very much again for accepting this invitation. And also I would like to thank all of you to join us for this event. And before we finish, may I kindly ask to all of you to quickly turn on your video camera so I can print screen and have this for our records. Okay, perfect. So thank you again, everybody. It was very nice seeing you, meeting you at least virtually during this event, and hope to see you in person soon enough. And please check the SCES 2020 website for the next events. Okay? Thank you very much. Stay well. Thank you. Yeah. Nice seeing you.
Thank you.
Bye.